The last two talks, and it's my pleasure to introduce now Marcelo Santos from the University of Campinas to talk about Riemann problems with delta shock waves.
Okay. Okay, so thank you. It's a great pleasure to be here and give this talk celebrating the 70th birthday of Dan. Okay. Ali. Before I start the slide, I would like to write something here. I think my talk is about, I'm trying to give some intuitive idea about the issue of my talk. So I think my talk is about concentration phenomena. So in 1D, so what I think by a concentration phenomenon, you have a point, and then we have something that is concentrating a point. And we know that the mathematical model for that is mathematical model. Is Dirac delta, introduced of course by delta, and the mathematical definition I think due to Laurent Schwartz is that delta P is the distribution so distribution that is defined in this way: phi of P with phi varying in the infinite function of support compact here in the R. So this is you can also put a weight. So you would have this. Constant, weight. So if you look this in 2D, so say in the half plane xt, so you can generalize that for a curve, say C, and if you parameterize this curve by xt, so you can define the Dirac delta function along this curve as a distribution that is the integral from 0 to t rho of t phi x t t dt. So I remember I think people is trying to use delta function in conservation law maybe 30 years ago. And I remember I said to a great mathematician that I was studying this, and he asked me what was the gain to do that. And I didn't know the answer, so I told him, well, I want to write a paper. So he thought, okay. And the conversation was finished.
They exist.
Sorry?
They exist.
Who? What?
The type.
Yeah.
Riemann problem delta shock wave.
Yeah, they exist, yeah. So now I'm going to take the risk to say something for great expert, that I think that nowadays I think that is very natural to think this in conservation law, and I think the phenomenon it may occur in conservation law because you can think. I don't have an example here, but maybe it's not complicated. You can have a conservation law with many characteristics just going to one point, and this point maybe can move. So you have a concentration of information in one point, and this, the way you can model this is using delta function. Okay, so I'm going to start my talk. I prepared 3 topics here. So this is the background saying about, forget this application. I'm not going to talk about application. I say in previous results, and then I'm going to talk some work that is in progress, and the first one is a joint work with Eduardo Abreu over there, and Richard de la Cruz from Colombia that is on the back, like that, yeah. Hi, Richard. Okay, and okay, previous results. Yes? So I put a question mark because I was not sure that this was the first result was this delta shock waves was used, Koshinsky. And if you look for Koshinsky in Google or in Math Science Net, we don't find any paper by him. What we know that he was a student of Cruz in Delft University. And many people cite his paper. And he considered this system here. And he showed that, well, the fact is that for certain state, left and right state, if you look the wave curves, there is no connection with one curve and two curves. So you have to use some other kind of solution, and that is delta wave solution. And usually what they do is to put, you have a region where you cannot connect. You have UL here, and you have UR here, say you cannot connect. And what you do is you put UR here, so you can connect, and then you approach and see the limit, and in the limit appears some delta function along the curve. Okay, so by classical wave, I mean shock curves satisfying Jardim Conneaut condition and rarefaction curve. This was this I already told. Koshinsky in his he made some numerical studies, and then he introduced this concept of shock wave. And in fact, the solution that he for the Riemann problem that he found for that system with certain states was a classical wave plus a delta, a direct delta along a curve. Okay. Well, as I told, there is no, this result by Koshinsky was in his thesis, which advisor was Cruz. And there is no paper by him, but other people cited Koshinsky, and Cruz, I think, continue studying his thesis. And I think the first paper after Koshinsky was this by Barbara K. Fitz and Cruz. I just quote here a small part of this paper where they mention Koshinsky thesis. So a system with this property. This paper here by Barbara and Koshinsky, I think it's very well known because it's a paper where he considered a system in which we have coincidence of angle value along a manifold. Okay? And so in this paper, he has a condition that the manifold where you have coincidence it's not parallel to angle vector. Okay? And in Koszynski paper, this happened. So in this paper, they don't, does not appear delta wave solution because they don't consider this possibility that the curve where there exists a coincidence of angle value is a rarefaction, is a rarefaction wave. Yeah. And the other paper where the Koszynski thesis cited is also by Cruz and Kefit. This was in a conference. So they claim that the singular solution of this type of this means shock wave delta function were first found by Koszynski. Okay. Okay. So let's go back to this Koszynski system. And I would like to point out that is not just an abstraction, just an example as disappeared. That is, there is a motivation for considering this system. You see, it's U square UV. And how can you obtain this system? Well, first you can consider the Euler equation of gas dynamics, putting the pressure and the density constant. If you take the Euler equations for gas dynamics and you put pressure and density constant, you obtain this system. So Koszynski system is when you put I equal to 0. Okay. You don't consider this dimension, right? Okay. This was pointed out in these people here, Dan Marchesin, Tong Zhang, and Yush Zhang in the journal. And so let me say what this authors did. So they did more than Koszynski. I think they wrote in the paper that they didn't know before the Koszynski thesis. And so they solved also the Riemann problem for that schism that Koszynski studied. They used also delta wave, but they did much more because they proved that this delta wave has a visco profile, considering this visco approximation that was introduced before by Dafermus or by Dafermus and Diperna. That the difference from the more classical regularization here, viscosity, is that here you put the variable t, and in this case you have also self-similar solution for the viscous system. And the solution with this, okay. The solution, I have a pointer. So the solution of this viscous system with this viscosity here, epsilon t, it's named viscosity wave fans. Okay, so they proved that the delta wave solution for this system here is the limit when epsilon goes to 0 of this approximation. And later on, and that's the reason because, well, there is two reasons because I work on this issue here, on this problem. The first one is that when I went to work at the Unicamp, a colleague of mine, Milton Lopes, had a student there, that's Gray Ercole, and he was doing his thesis on this subject. The second reason why I studied this is because Richard came from Colombia and he learned that also there. Okay, but then Gray Ercole, in his thesis, he considering related a more general system, but is not does not include the Koszynski system in the whole plane UV because this condition here. But for this system here, he also proved that you have convergence of viscosity wave fans, that viscosity wave fans are a solution of this system. They proved that if you put epsilon t uxx here and epsilon t vx here, and you can pass epsilon to 0 and you obtain delta wave solution. Okay, so now I'm going to pass to the second topic of my talk. So how much time, when should I finish?
Until 1:15.
Sorry?
So 15 more minutes.
15 more minutes? Okay. So solution system, this system here is a 3x3 system. So, okay, this system here has a constant. And the Riemann problem with delta shock wave was solved by Richard, that I point him there, with all the people from Colombia. Okay, so now what are you doing? What are you doing now? Now we want to because Richard and others solved just the Riemann problem for this system. And now you want to obtain this Riemann solution with delta waves as a limiting or as a numerical approximation. And this we are doing joint with Eduardo Abreu. And so I had no time, or I didn't know how to put this here, so I'm going to open another file here. And so these are some numerical tests about this system, and this was doing using a numeric scheme developed by Johannes, Paris, and Eduardo Abreu. And so what's interesting here is if you consider a numerical approximation, then you see very clearly the shock in developing as times evolve. So here you can see the concentration of some variable. I think this Eduardo and Richard can explain better than me. Yeah. Okay, so we Richard implemented this numeric scheme, and as times evolves, you see more and more a delta function appear. Okay, so it's I think it's natural. Okay, so Richard made some experiment with that, and there is a summary here. Yeah. Okay, so coming back to here. As I told, the first reason I'm studying this subject is because when I went to Unicamp, Greer Cole was there, and he was studying this. And after his thesis, we started discussing the subject, and in that time, there was a paper by Hermano Fried and Shane on asymptotic stability for Riemann solution. And so we tried to follow this paper, and we obtained some partial results that we don't think is ready to publish it. But the point is that okay, so we consider the system that Greer Cole studied in his thesis, and then here we show how to construct the delta wave solution. Okay, so very quickly. First, you construct the curve where the delta appear, the delta wave appear. That is exactly the Rankine-Hogoniot curve for the first equation, because the first equation does not depend on the second variable. So you can solve this, okay? And you have this curve, and then you have to solve the second equation with u here. And then what you do, following a paper by some other people that is here, Dan, Zhang, and Yushi Zheng, the same paper I mentioned before. So what we do is we integrate the second equation with x, and so the integral of v we call w, and you have to solve, you can solve this equation using the characteristic method. And here is the explicit wave, delta wave solution. We have the explicit formula. And then the definition of asymptotic stability given by Fried and Hermano is that you give a perturbation of the Riemann data, and the solution for this perturbation you call u, and then you look this u along the radius and integrate with respect to the t, and then you pass the limit. So in average it has to go to 0. Okay. So the result that we have is that we made a perturbation the second variable, and then we can prove that this limit goes to 0. Okay, it is just to make some computation. Okay. Did I? 7 minutes? Okay, so I would like to use the last 5 minutes to say congratulations to Dan, and I have many reasons to say thank you to him. And the first reason is that I was very happy that in the decade that in 1980 that I was doing my PhD here, Dan moved from PUC to IMPA. And in that time I was doing my PhD with Frido, and I think I can say that Dan was a kind of co-advisor. And maybe you don't remember, but before my defense, you spend, I think, 2 hours every day listening just to me presenting my thesis in one of the rooms in the second floor, I remember. And my thesis was about compensated compactness, following Poitacan thesis that was a Gleam student. And I remember that you told several times to me, this is very complicated, this is very complicated.
I agree.
But when there was only 15 days to my defense, I was presenting something about metrics. We have to compute something about metrics. No? And I just told something to him, and he told me, that's maybe true, but perhaps it's very difficult to prove. So you should prove it. And I went to home and tried to prove, and it was very difficult. It was an elementary question. I don't remember the question, but it was an elementary question. And when there was only 1 week to my defense, I had not proved yet. And Armando was very mad with me, because he was very nervous, because everything was... But just I think 2 or 3 days before the defense, I solved I could prove it, and then I showed to Dan. So this one reason I thank Dan, and there are several other reasons. Dan organized the first workshop here at IMPA on conservation laws. And on the first workshop, I think well, I don't remember workshop. And the first workshop here on hyperbolic problems at IMPA. So it was here Glim and many very old important people. I think Kevin also here. And Glim, joint with Glim also came Poitacan, in which thesis my thesis was based on. I was lucky to meet him here, and in that time, as just Kevin was telling, we used reprints, right? We could not send by email. In fact, in the 1980s was the decade that appeared email and the latex also. Yeah. And I saw I had to talk with Poitacan, asking him to send me his thesis. And I was lucky that Cido, that is not here, Aparecido Jesuino, went to Courant, and then when he came back, he brought me his thesis. And in the second workshop, Glim also here. So I would say this first workshop implied my thesis. And the second workshop, Glim was also here, and Blake Temple. This I remember very well. Okay, and in the second workshop, I was with my thesis ready, and I had the opportunity to present my thesis there. And Frederico also was in this here. Our friend Fred Furtado was here in O's workshop, right? And I was, I think, very nervous, and Dan asked me a question that I could not answer that time. You asked me, what's the difference between your thesis and Poitacan thesis? And I just became quiet and thinking about the answer. And that time I didn't understand because I was thinking, my system is different from Poitacan's system, so what he's asking now? And then I learned something that I always try to pass to my students, that what matters is not the theorem, the statement, it's the proof, right? So, and I didn't answer his question, but later on I learned the answer. And I thank you also because at that time you introduced me to Blake Temple, and you told me to ask him to be a postdoc with Blake Temple. I didn't do the postdoc with him, but he talked with Jonathan Goldman at Curat, and Jonathan Goldman, then I wrote to Jonathan Goldman, and then I went there. Okay, so this implied in postdoc at Curat. Okay, yeah. So I have many other things that I would like to say to thank you, Dan, but I think my time is over, right? 2 minutes? Okay, so I have very good memories of Dan. One of that is related to the work with you, because in that time you used to have seminar here in conservation law. And when I want to see if Dan remember now, because when I think you started this Palmeira manifold, no? And then present to us in a talk. And so he started the talk, I can see, he started the talk doing this, and then he asked us, what's this? So nobody answered, and so he told, oh, let me see if I can. Okay, and what's that? So still nobody could answer, and he told, this is an elephant. You don't remember?
Of course not.
Okay, he told, this is an elephant if you see him from the back, you know. So he told, what are you doing now is showing the elephant, no? It's not just the project. Okay, okay, so I thank you all, and this is my daughter. Okay. Okay. Alexei. Okay. I don't know. I don't know if you were here at the beginning of my talk.
I'm sorry.
Okay. Yeah. That's something that, in fact, I don't know. I just it's some naive idea that I think that. You mean about this here, right? Right, this concentration, is that what you are asking? Yeah. So I don't have a technical answer for that, okay? Yeah. So if you, when I was preparing my talk, I read some papers, and I think I saw something related to that, but yesterday I could not find an example. But there is a book by a group of Chinese people where a chapter is on delta wave function, and they, well, 30, huh?
There's perhaps a few papers you're missing.
Yeah, of course, in my talk, right? Yeah.
There's an Israeli guy who has half a dozen papers on this. I'm trying to remember his name. He changed name. Remember his first name.
Sever.
Exactly. S-E-V-R-E-R.
S-E-V-R, okay.
His name was Michael Monk.
Yeah. People are saying that you have, they found the application of this in physics and engineering, in cosmology, you know, these concentrations. Where it disappears also is in Chaplin model, of gas dynamics, it's in cosmology. Yeah, okay. So. Okay. Maybe you have, you know better. Okay. Okay. Okay.
You inject it at x equals 0. You have a source there. That's it. Suffice. Put a lamp, make a hole in a pipe, and it squirts. And you get a normal pipe.
Remember that we had for the allocations.
It's not that different. You're right. Everything is all the same.
In the end, everything is the same. It's physics.
That's its conclusion. Everything is all the same.
Say it again.
Tudo é a mesma coisa.
Tudo é a mesma coisa. Okay.
Funciona.
Yeah.
Okay, so other questions? Let's speak again.
Okay.